Let's take a look at a remote control doorbell. Let me zoom down in this and bring the items into shot. So this is USB powered. It plugs into a USB power supply and you can assign various buttons and you can assign different tones as well, as I'll show you. So say for instance, and I've turned the volume down in this, you press this one. This is the button that comes with it. It does that one. You have a siren and you have a chime and speech. After that, it all gets a bit wild. It starts going into the very long tunes. Let me just skip through a few of them. So it does all the hello, welcome in different languages. And then it does these huge tunes. Now, I could be wrong here. I'm just going to actually mute this now by pressing that. I could be wrong here, but to me, a doorbell should just basically go ding-dong. Or it should basically be a cascade of chimes, but playing long sections of music. It's the sort of thing that by the time you've answered the door, the thing will still be playing in the background. It's very odd. But anyway, let's try, what was that? Let's go into, say, let's skip through a few. I'll skip through them. So we'll go to a music one, and I'll show you how to program a button. So you press and hold this button here. That's the speaker button, and then you press a button. Oh, this is such a noisy. I'm going to mute it down a bit. It does have multiple volume settings. So see, theoretically now, this one's doing this tune. This one's doing the siren. This one's doing the chime and speech. And this one is doing music. It takes a lot. Now, the question is, how do you delete them all? To delete them all, I'll describe what you've got here. You've got a button marked to the speaker, and that actually does the volume. I shall press it, and you'll hear the volume change. High, medium, low, and off. But the off, the thing flashes on and off very dimly. Right, tell you what, I'm just going to put my hand over this to mute it, and we'll go down to a lower setting. So to program these, you press and hold the speaker button, the volume button, but if you want to delete them all, this is not documented. Watch this. This is glowing at the moment. I don't know if you can even see that. If I press and hold it, you'll hear it beep, and that's the point it would program a new button. But leave it, and this starts flashing. Then release it. And once you've done that, it's deleted all the codes. Okay, so now we've seen it operate. Let's open it up. It's quite nice to kind of multiple codes. The siren one could potentially be used with the code transmitting passive infrared detector. So you could actually have something that sets an alarm off if someone goes into an area. Is this in focus? Oh God, that would be so annoying to go into prepare the video for upload and find it was all out of focus. If it happens again, I'm going to be very annoyed. Okay, so what do we have here? We have the little speaker here. Is this going to come out, or is this glued in? It may be glued in. Nothing in the back. We've got the buttons. We've got 3 chips. That one is next to the antenna, so I'm guessing that is the antenna, the RF receiver chip. I'll tell you what, I'll take a picture of it, right? And then we can take a closer look. One moment, please. Reverse engineering is complete. Let's explore. And one thing took me by surprise. I wasn't really expecting it, but it does make sense. I realised that this was going to be an RF receiver. I thought this was going to be the brains of everything, and this was just a simple amplifier, but it turns out this is an FMD microcontroller. It's a clone of a PIC, and this is the bit that's doing all the magic. This stores all the speech and the music, and there's a couple of extra pins that are not connected. Well, I had to probe and explore. If you take these high, you can trigger it, and you can also select the music, so it has the network facility, a couple of data lines, but it also can be operated on its own just with a speaker connected, battery supply, and just buttons going into it. Other oddities on this circuit board. The incoming supply from the USB, there's a couple of resistors here that you might associate with, say, for instance, USB-C. But because there's no USB-C connector fitted, they just go to pads on the back, but they're not connected to anything. But if it was fitted, it would be the resistors that enable the power output. The incoming 5-volt supply goes straight through a diode for polarity protection, which is novel. There's a transistor that switches the 3 LEDs that flash, but there's a 1K resistor in series with them, with all 3, which are in parallel, which means that they don't light very brightly. And if that had been, say, for instance, a 100 ohm resistor, or perhaps maybe a bit higher, that would have actually worked better. It would have been a good intensity for its intended purpose. There is another oddity, and this is for the audio, not the audio, the RF geeks. Here is the onboard antenna snaking across here, and then they've just soldered on a coiled antenna onto this connection where it goes into the RF circuitry, which means that effectively it's got 2 antennas connected to the same input point. Anything else worth mentioning here? There is a programming port. And that is it. The thing that wasted the most time in reverse engineering this was realising that the FMD is such a ridiculous clone of the PIC microcontrollers, like embarrassingly obvious clone. Right, tell you what, let's take a look at the schematics. And it's a 2-page schematic this time. We shall start. I've just dropped that picture, that's fine. We shall start the RF section. So the incoming USB supply goes through the diode. There is a capacitor before that, and there's the 2 resistors going to the negative rail for the USB side. There is, I'll just call it plus 5 volts. Not 5 volts, because it's got the diode drop. So let's say plus, say about 4-ish volts, plus volts. And the chip here that I tried writing the number in here, and I've had to cover over it and put it down here, CMT222OLS. When I typed that in, didn't immediately get a hit because for some reason I typed in CMT22OLS, and then I wrote the number up here, did it again. 3 2s. Tricky. Anyway, once you type in the 3 2s, then you find a hit. It's a very standard chip. So here are the 2 antennas. I would have thought that's counterproductive. But anyway, they come to the input here, and then there is a tuned circuit filter. Then it's capacitively coupled, and there's a bit more filtering, and then it goes to the chip, which has the resonator. Hold on. Where is that? The resonator, which is marked 13.52127 megahertz, so it's kind of multiplying that up to get the 433 megahertz this uses. So it's got the resonator, it's got a capacitor for internal use, it's got the negative connection, a shut pin, they call it shut. If you take it high, it disables the RF receiver. If you take it low, it enables it. And then for power, we've got a 100 ohm resistor going down to capacitor to provide it nice, stable, decoupled power. And then the other pin from it is data out. There is another pin that's just not used. It's marked not used, but they'd actually tied it. So I'll draw it here to ground. Not used, but they just grounded it. It was right next to the oscillator pin, which kind of makes sense to have that grounded as a bit of extra screening, maybe. Let's go on to the next page, which has the plus volts, the 0 volts, and then the data coming in. And by a miracle of incompetence, I've not shown the data coming in. Hold on. Data. In. There we go. Now I have. So the FMD, Fremont Micro Devices, FT60E011A, I looked at the data sheet and wow, it really is. It's such a clone. Say, for instance, the only thing they've really changed is that the Arizona microchip, that's showing my age here, calling them Arizona microchip. The PIC microcontrollers, the instruction set, refers to an 8-bit byte as a file. So they just changed the word file to register. So say, for instance, you've got commands like decrement file skip of 0. They've changed it to decrement register skip of 0. And also, when I looked it up further, there was over in the EEV blog forum, there was a discussion about the Fremont Micro Devices and the programmers available for them. Very poorly documented, mainly in Chinese, which doesn't help. But the development system is actually just the original, an older version of MPLAB, which is Microchip's development system. In a way, that would work better for me because the newer version of that was complicated. But anyway, because they've used all the pins, one of the pins is the master clear, and it's also used for programming, higher voltage programming. You can't normally have a pull-up, internal pull-up in that. So they've used an external pull-up resistor here, 10k resistor on the button for that input. There is another button which doesn't need that. It's got the internal pull-up. Then there's a transistor being driven, which can drive the LEDs. They didn't really need with an NPN transistor to have the 10k pull-down resistor, but they've used it. Then we've got the two data lines going across to the doorbell chip. There's a resistor that would be good if they just lowered the value. Let's compute that right now. So what colour LEDs? I'm trying to remember what colour they were. They were red. So the voltage crossing would be 2 volts. Say after the diode it's going to be 4.4 volts. So 2.4 volts to drop. And we want, say, to run those LEDs at, say, 30 milliamps. R equals V divided by 0.03 equals 100 ohm resistor would have been absolutely perfect for that. Instead of that, it would have run the LEDs much brighter. But then there is maybe they just allow for it not having a high standby current. I don't know what the standby current is for use on power banks. Hold on, let's test that. This is going to make a loud noise, so I shall take it off screen while I plug it in. What we got? Standby current 11 milliamps. That's not bad. That'll give you a modestly long runtime. Put that back out the way. And here's the doorbell chip, which has a couple of decoupling capacitors. Rather than clutter up the drawing, I've shown this is the 0 volt, the little ground reference, and I've shown them there. And it basically has the two data lines in. It's got the decoupled power, because it is going to be driving a speaker with probably a little H-bridge inside. And then it's got those two auxiliary inputs that I suppose you'd be better using a resistor with them. But you could theoretically, and this isn't, but I suppose it is official because it did it when I tried it. You could basically just have manual control over that chip. But there we have it. One other thing that's worth mentioning, the remote button with it is odd. I did open it up. Similar circuitry to one of these, which I've shown, almost identical circuitry, but boosted up somewhat because instead of the two 2016 lithium cells in here, this one has a stack of three 2016 cells, which means it's basically got a 9 volt battery in it. That's just to increase the range. But there we have it. It's a very cheap and common little doorbell circuit. And it works. It's nice that you can assign multiple tones. So say for instance you could have like multiple doors to a building, and when someone pushes the appropriate button it just plays the tune for that particular one. But what I would like to see is just, instead of all the long musical tunes, just basically just series of chimes that were distinctive but short, so that you know by the time you answer the door it's not blasting away with music in the background. But there we have it. The hideous little remote control doorbell. It's actually quite nicely designed, and it does actually work, which is good.